Alright, the last thing I want to talk about in this notebook of the multiple finite elements is the following. Okay. So the question is why are the commercial packages that can write my own frame program? And what you'll see later in this course, I'm going to give you a two-dimensional finite element code that is as good as ANSYS two-dimensional finite element code. Okay, it's not going to be maybe as sexy with the GUI and stuff like that, but it's going to be the same functionality to a large extent. So you can really write your own finite element code with it. So 1D, 2D, or 3D code. You don't have to buy it. Okay, but why do we go and why do we buy it? Because I'll tell you the reason is the GUI. It's very easy and accessible. And to work with a GUI and say, let's specify loads, let's do stuff, and all of this stuff that we've learned here about consistent loads, numbering, meshing, and all that stuff is happening by itself in the background. Okay, this is the primary reason. The second reason is this code has been verified and validated. Okay, there might be a bug in my code. I haven't properly checked it. I showed you how easy it is that we could hard code something wrong, like the area. Okay, so it's possible that there's some bugs in the code, and you won't pick it up unless you've done proper verification and validation. This is the second reason why you will buy a finite element package. What is verification and validation? This is a critical part that you have to understand. And this is also whenever you use the finite element method, you're going to have to verify your answer. Okay? And if you want to use your finite element approach to model something in real life, you're going to have to go and validate your answer. And let me quickly show you what I mean with verification and validation. So NUFIMS is the North American Finite Elements Methods Association. Okay, it's an international association, and they also accredit the finite element specialists. So you can actually go and write an exam with them, and they'll certify and say this guy or girl is a fantastic engineer. They can model fantastic, so they are a NUFIMS certified finite element analyst. Okay, so they certify analysts as well. Let me show you what is this. Please go and click on this VNB. This is going to tell you what is verification, what's validation. Verification, just in short, before you go to those slides, I just want to tell you that you just, what is going on there, know with what ears to listen to. Verification is making sure that you've implemented the mathematics correctly. Okay, so verification is the process that the mathematics that you're doing is correct. So that's exactly what we've been doing in the course to a large extent, is saying, what is our expectation from the solid mechanics point of view, and what is our expectation from the finite element solution point of view? Okay, and that we can verify that those two things make sense. So we've done verification quite a bit already. But verification is if you were to write your own code, you want to make sure you can double check that it's properly verified. That when you meant to do x squared, that you did do x squared, that all the mathematics is correctly implemented. And validation is we're going to use this finite element now to model something in real life. But it might be that it's completely inappropriate. The model that we use, the mathematics is correct. The model is correctly implemented. Everything is hunky-dory. The reality might be that, whoa, the question is the model appropriate? So for instance, if I want to model a car crash, okay, and I use a linear elastic finite element model, and I try to validate my answer, what I'll see is the car crash, there's glass, there's permanent deformation happening. If I look at my finite element result, the stresses go to near infinity, and in the end there's no deformation, no glass, nothing, no crumbling, no permanent deformation. All that energy that goes in the crash into strain energy gets released again. And so when you do this validation process, the question you're asking is the model that you've chosen appropriate for the reality that you're trying to model? That is really what that boils down to. So let's go and open up what verification validation is. Please go and download this and read carefully through this. This is really important. And not only for MKM 321, but as an engineer in future. Please take note about NUFIMS. I'll talk about one or two other things about NUFIMS in a second. There are aspects about NUFIMS. They do courses as well. If you want to extend your finite element knowledge, for instance, in terms of composites, or in terms of computational fluid dynamics, or in terms of dynamics, or in terms of nonlinear geometry or plasticity, they do courses that you can do online, and then you can get certified as well. Okay, so let's just quickly check here. So this is here talking about some of the overview of activities of NUFIMS. And the reason I do this is I'm not a rep for NUFIMS at all. I used to be a member of NUFIMS when there was still finances available for that, but at the moment I'm not. But I still believe in their course, and this is really where you as an engineer will learn the problem specifics of how to model. Okay, So you can see a composite finite element analysis. So practical CFD that they do a lot of things. 10 ways secrets to professional value engineering industry. Dynamic finite element analysis. Model analysis and virtual product validation. There's FAM, Advanced Research Industrial Application for Experimental Mechanics. Okay. There is power generation, engineering challenges in low carbon future. Practical CFD analysis. Multi-physics simulations using implicit sequential coupling. So what multi-physics is when you start coupling finite elements with this fluid solvent. Now you can have fluid structure interaction, and maybe this electromagnetics. Now you have fluid structure and electromagnetic interaction. So you can imagine if you want to model a plasma in a reactor, for instance, that is quite a lot of physics that are involved. Or often in metallurgical engineering, when you have sort of thermal effects, you have chemistry, chemical effects, structural effects, all of those things interacting in one go. There's also a lot of things that's related a little bit to codes, for instance, creep loading, pressure components, fatigue, and welded pressure vessels. So there's a lot of these additional parts and courses that they offer where you can really specialize in a specific thing. Say, I really want to become a composite boffin and how to model that. Then you can do a couple of their courses. So please go and check out the webinars and the courses that they have. Okay, so so these were actually the webinars here, but here's an example of some of the courses: dynamic FE, nonlinear, composites, optimization, and all of these things. We can sort of do optimization inside this. Okay, so this is really to make sure that you understand that. Okay, where's my verification validation? Okay, so in the end, this is just an end example talking about verification validation. There's actually a third thing. There's V and V and Q, verification, validation, and qualification. So when you also do the report writing, that is in the documentation, it's critical in simulation as well, so that you can in the end show to the client, here's my documents of what I've done. So please note that verification validation is sort of the older version of things. There's also qualification that's really becoming important in terms of computational solid mechanics. Okay, so computational mechanics, the use of numerical approximation to solve mathematics based on models of physics of interest. Okay, so this is really what we've learned in this course, and I've hammered this point that we need to understand what the approximations characteristics are in terms of what is the models of the physics characteristics that we expect, and then obviously what is reality, the expectation from reality point of view. Okay. That's fine. I'm just going to go into all these things. All right. So this is again classical George Box quote. Actually, a couple of years ago, I gave a talk at Tsinghua University in China, and the talks was based on this title: "All models are wrong, but some are useful," and it was fairly well received. This talk about just to reminding ourselves that we need to maybe have sense in the way we model, as opposed to just going more and more complex in our modeling. Okay, so that's just in terms of what's going on. Verification is the process of determining that a computational model accurately presents the underlying mathematical model, so that the maths is correctly proven, the numerics is correctly solved, all that type of jazz. This is verification. Okay, so that we're computing correctly. Are you using your calculator appropriately? Do you know how to not make a mistake and stuff like that? Validation is the process of determining the degree to which a model is an accurate representation of the real world. So this is what we spoke about in terms of that car. A linear elastic model for a car crash is completely inappropriate because the major physics is completely wrong. Okay, so it's very limited questions that would find that model useful. Okay, and it brings us back to George Box's quote: "All models are wrong, but some are useful." And this is really the essence that I just want to leave you with this part is: think about the question. The question will dictate what is an appropriate model. It's not just having a model that can do with all the bells and whistles. You want the simplest model, because then you also require the least amount of data that you have to supply. There's no point in having a complex model and you're guessing a lot of the parameters. As a matter of fact, there are many simulations where the models are complex and worse off than a simpler model where you've only supplied the information that you actually had at hand. You didn't guess any of the other parameters. Don't forget that point. It's easy to have a model that's more complex and worse than a simpler model. Okay. So this is really, and what this is really all about is the question will drive the appropriate model. So start with the question. What do you want to do with the model? That's the first place where you have to start. Okay. Then there's a couple of verification examples here, validation examples, so that you can go, and please go, I'm not going to go through this whole slide, but please go and work through this, read through it. It's quite an interesting webinar series on this verification and verification and validation, and like I say, also qualification. that is critical. Okay, so there's giving you an idea of a lot more of the details behind this. Okay, and this is also something that NASA is quite important from governmental kind of agencies like NASA, etc. In terms of that they can have quality models, because it's in the end having a finite element package in your hand is can be dangerous as well. And I'm going to remind you again, any high school kid can now operate a finite element package within a week. Yeah, you need to be able to distinguish yourself from that high school kid. And if I give a high school kid 2 weeks, they'll do it faster than you. Okay, so the question is, what's going to distinguish you from that high school kid? And I would not trust an aircraft that was designed by a high school kid using CFD. And you shouldn't either. And why is that the case? Because there's a couple of things that's part of verification validation that would be missing, that the high school kid would not be applying. So please make sure that you're comfortable with these ideas and understand the rationale behind them. I'm going to leave you with this George Box quote. It's quite a famous quote. There are a number of other quotes that one can talk about, but this is really, I think, an essence that you just have to remind yourself of, that all the models that you will build will be an approximation. So you need to make sure that the things that you approximate are such that it's still useful. Okay. And that sort of leaves us for the end of this part of the one-dimensional finite elements. When we talk again, we pretty much going to be hopping onto the two-dimensional, extending our one-dimensional knowledge to 2D FEM and start operating a two-dimensional Python finite element package that we can have fun with and learn some lessons. Also see how things can go wrong if you're not careful. Thank you.